Before we start talking about trigonometry and the trigonometric functions, I want to take a few minutes to review some basic concepts from geometry. This Geometry Review Part 1 handout is posted as a PDF in Canvas. If you'd rather just read it over on your own, that's fine. Then you don't need to watch this video. And I hope all these ideas should be a review for you. Just reminding you of things from lower level math courses. So let's get started here with number one. An angle consists of two sides or rays that meet at a vertex. The size of the angle is not affected by the length of the sides. We often think of as an angle as being represented by a rotation from an initial side to a terminal side. It's like if I place my ruler here along one side with the end at the vertex, I can rotate the ruler to the terminal side of the angle, and that rotation is a way of thinking of what the angle represents. We can measure the size of an angle using degrees. A right angle has measured 90 degrees. There's a right angle right here pictured. A straight angle has measured 180 degrees. A full circle rotation has measured 360 degrees. And it's probably just worth noting that we can think of some of these angles as multiples of 90. 1 times 90 is a right angle. 2 times 90 is 180, so a straight angle is like 2 right angles added together. 270 degrees is 3 times 90. That's like 3 right angles. And then 360 full circle is like 4 right angles. 4 times 90 is 360. 4 right angles added together. An acute angle has measure between 0 and 90 degrees. An acute angle is narrower than a right angle. It's kind of pointy and sharp, right? An obtuse angle has a measure between 90 and 180. An obtuse angle is wider than a right angle. Two lines are said to be perpendicular if they meet at right angles. And triangles are three-sided figures. The three angles of any triangle add up to 180 degrees. And that's a really important fact, because if we know two angles of a triangle, we can always use that to find the third angle. And it's kind of interesting. No matter what the shape of the triangle is, the angle measures will always add up to 180 degrees. Kind of a profound fact there. Also, I state here that the longest side of a triangle is always across from the largest angle, and the shortest side is always across from the smallest angle. So like in this third example here on the right, there's that 120 degree angle is the largest angle, and across from it is the longest side of that triangle. Sometimes that's a useful fact to make use of. A right triangle is a special kind of triangle that has a right angle, so it must have a 90 degree angle. And in fact, there's a special symbol we use for 90 degrees. This little square shape in the corner of these triangles, that is a way of representing a 90 degree angle. So we have a 90 degree angle here, here, here. Also, I use that square shape up higher up on the handout. The two sides of the right angle are called the legs of the right triangle. So here's one leg, the other leg. They can be different. They could possibly be sometimes equal. And the side opposite the right angle is called the hypotenuse. So here's the hypotenuse of this triangle. And because the 90 degree angle of a right triangle is always the largest angle in that triangle, the hypotenuse, the side across from it, has to always be the longest side of a right triangle. The hypotenuse is always longer than both of the legs. Let's move on to the next page. And one theorem that we're going to use quite a bit and all the way through this course is something called the Pythagorean theorem. It's incredibly important for us. The sum of the squares of the two legs of a right triangle is equal to the square of the hypotenuse. And that picture on the previous page is an illustration of the Pythagorean theorem, because in this right triangle with sides labeled ABC, A and B are the legs, C is the hypotenuse, and I think you're familiar with this equation, A squared plus B squared equals C squared. One of the most famous theorems in geometry. And the way we're going to use the Pythagorean theorem most often is as follows. If we know two sides of a right triangle, we use this theorem to find the third side. So don't forget, the Pythagorean theorem only applies to right triangles. So if you do not have a 90-degree angle in the triangle, you cannot use the Pythagorean theorem. And okay, next bit of vocabulary here. Any two angles are said to be complementary if their measures add up to 90 degrees. The two acute angles of any right triangle are complementary, right? Because in a right triangle, you got to have a 90-degree angle. That leaves 90 degrees for the other two angles. They got to add up to 90, and so they're complementary. Any two angles are said to be supplementary if their measures add up to 180. Supplementary angles add up to a straight angle. So a couple examples here. 20 degrees, 70 degrees are complementary. 50 and 130 degrees are supplementary. And I'm not a big fan of piling on lots and lots of vocabulary, but these really are a couple words that we want to keep straight. So just make sure you have some way of distinguishing complementary, supplementary. The way I've always remembered this is C comes before S in alphabetical order. 90 is smaller than 180 when I write those numbers in order. So C goes with 90. Complementary refers to two angles that add up to 90 degrees. S goes with 180. Supplementary refers to angles that add up to 180 degrees. That should be enough for you to never get those words mixed up again. Now, we're going to have to talk about the idea of similar triangles to get started in this course. Similar triangles have the same shape, but possibly different sizes. Similar triangles have the same angle measures. And any two triangles that have the same three angle measures must be similar to each other. Sides of similar triangles are proportional. So what does that mean when we say that sides are proportional? So I drew some triangles that I know are similar because I drew them myself. And I labeled the lengths of the sides here. 5, 4, 6 for the first one, 15, 12, 18 for the second, 2.5, 2, and 3 for the third. One way to think of what it means for the sides to be proportional is you can get the relationship between the sides of two different triangles is always going to involve a constant multiple. In other words, 5 times 3 is 15. The 15 side corresponds to the 5. So if I multiply the other two sides of this first triangle by 3, I should get the corresponding sides of the larger. 4 times 3 is 12. 6 times 3 is 18. So 3 is sort of this constant of proportionality that relates those two triangles. You can also see the first and the third, how they're related. The sides of the third are actually half the size of the first triangle. If you divide the sides by 2, you get the sides of the third. You can also think of that as multiplying by a half or 0.5, right? 5 times 0.5 is 2.5. 4 times 0.5 is 2. 6 times 0.5 is 3. So that also illustrates when you get smaller, you're multiplying by a smaller number, you're actually dividing, right, to get the corresponding sides. Now, 11 is a statement about right triangles, and it's kind of a mouthful, but it's not that profound, but we should talk about it. If an acute angle of one right triangle has the same measure as an acute angle of another right triangle, then the two triangles must be similar triangles. So we're already talking about right triangles, so they both have a 90-degree angle. And so we're saying if they have a second angle that's equal, so if an acute angle of one equals an acute angle of the other, then of course the third angles must also be equal. So the three angles of one match the three angles of the other. The triangle's got to be similar. So there's sort of this special property for right triangles that if all you know is one acute angle of a right triangle equals one acute angle of another right triangle, they automatically have to be similar triangles. And finally, the 12th statement here, the ratios of corresponding sides of similar triangles are equal. This idea applied to right triangles is the basis for our mnemonic SOHCAHTOA, which will be our starting point in trigonometry. And I illustrate that with a picture here of one right triangle. These are both right triangles. One right triangle has angles 90, 75, 15. This other one has same angles, right? 90, 75, 15, so they got to be similar. And when we say that the ratios of corresponding sides are equal, well, I labeled these sides A, B, C, D, E, F. Now, A is definitely bigger than D, B is bigger than E, C is bigger than F. They're not equal. But if I divide A divided by B to get a fraction, that will equal D divided by E. So these ratios come out to be equal. A divided by C will equal what you get when you take D divided by F, and so on and so forth. B divided by C equals E divided by F. That's just an important principle, because we're going to talk about how these trigonometric function values that we look at don't depend on the size of the right triangle we're working with, because these ratios come out the same as long as the triangles are similar. Just want to refer back to these triangles that were up above to say a little bit more about this ratio of corresponding sides. And that, remember, these were similar triangles. The ratio, one ratio that I get from the first triangle is 5/4. 5/4 is actually 1.25, right? Now the corresponding sides of that second triangle are 15 and 12. 15/12 is going to reduce to 5/4, which is equal to 1.25. And on that third triangle, if I take 2.5/2 and divide that out, I also get 1.25. So while the individual sides all have different lengths, it's these ratios that come out to be equal because the triangles are similar. Okay, so that's, I think that's the end of this geometry review. In our next video, we'll be ready to start working on trigonometry.